In this section, we're going to learn about some of the acidic and basic properties that cations and anions can have in water. You might remember from last semester, we learned that when you have an acid-base reaction, you always produce a salt and water. This is called a neutralization reaction, where a salt refers to some ionic compound composed of a cation and anion component. Just because it's called a neutralization reaction doesn't actually mean that every single salt that's formed actually leads to a neutral solution. So we're going to learn how you can distinguish between acidic salts, basic salts, and neutral salts, and how you can use your acid-base ionization chart to help you. The pH of the resulting solution after neutralization is influenced by the stronger partner. So imagine that we have an acid solution and a base solution, and they're both the same molarity, and we're going to mix together the same amount, so equal amounts of them. And if we have a strong acid with a strong base, we end up producing a neutral solution, or one that has a pH equal to 7. If we have equal molar strong acid and weak base, and we mix together the exact same amounts of those, the strong acid is essentially the stronger partner there because it's getting mixed with a weak base. So the type of salt that we produce will actually interact with the water and produce an acidic solution where the pH of the solution is less than 7. If we mix together equal molar amounts of a weak acid and a strong base now, the strong base is the stronger partner, and it'll essentially take over the pH because the salt that it'll form will lead to a basic solution, and the pH will end up being greater than 7. So all three of these reactions represent acid-base neutralization reactions because it's an acid-base neutralization reaction if you have any acid reacting with any base. But it doesn't mean that you're always going to end up with a neutral solution. Only if you have a strong acid reacting with a strong base will you form a neutral solution. Let's start with salts that give neutral solutions. A strong acid plus a strong base will produce water and what's known as a neutral salt, a salt that will not react with water and change the pH. So an example of this would be hydrochloric acid, which is HCl, plus NaOH, sodium hydroxide. This is a double replacement type reaction. We would form water, and the salt that we would form would be sodium chloride. We want to take our salt and break it apart and look at the cation component and the anion component. The cation component is going to be the sodium ion. The sodium ion is neutral, so it doesn't change the pH at all. Metal cations that come from strong bases are going to always be neutral. Since our metal cation is sodium and it came from sodium hydroxide, that's going to be a neutral cation. The anion component of our salt, sodium chloride, is Cl-. The chloride anion is also neutral. Conjugate bases of strong acids are very, very weak bases. The chloride anion is a very weak base. It has no desire to go back and pick up a proton, so it doesn't. It just stays chloride anion, which is why it ends up being neutral. The following ions will yield a neutral solution. Anions that are conjugate bases from strong monoprotic acids. So this is a truncated version of our Ka-Kb chart, and if we look at the top, we have our strong acids listed. So we're going to hone in on the acids that are up here. And we only want to talk about the monoprotic ones, so hydroiodic, hydrobromic, perchloric. We'll skip over sulfuric for now. Hydrochloric, nitric. These are examples of strong monoprotic acids. You can tell they're strong because the Ka is just listed as large. There's no numerical value given. We only are given Kas for weak acids. Now, the conjugate base or the anion of any of those strong acids, notice the Kb is very small. That's because all of those are very weak bases. So iodide, bromide, perchlorate, skipping sulfuric acid again, chloride, nitrate, all of those anions are examples of neutral anions because they are the conjugate base of a strong acid. So they're happy, they're stable, they're not going to react further with water, which was the other product from a neutralization reaction, to change the pH at all. And cations from strong bases. So strong bases we learned are group 2A and group 1A metal cations usually. So some examples would be the lithium ion, the sodium ion, potassium ion. From group 2A we could have magnesium 2+, calcium 2+, strontium. So if we had magnesium hydroxide, which is MgOH2, and that breaks up into magnesium 2+ ions plus 2OH minus. The magnesium is the cation from that strong base. So it's not going to react with water and change the pH at all. If we have something like hydroiodic acid, that's a strong acid that dissociates into H+ and I-. The iodide is the conjugate base of our strong acid. And so that guy is not going to interact with the water product from the neutralization reaction, changing the pH at all. So those are going to be things that you want to understand how to look at your Ka, Kb chart and figure out what type of acid or base you have, where your strong acids live, where your weak acids live, and be able to distinguish between them. Salts that give basic solutions. So if we have a weak acid and we mix it together with a strong base in a neutralization reaction, we'll produce water and we'll make a salt. In this case, the salt will be a basic salt. So let's put some actual acids and bases with these. Hydrocyanic acid, HCN, is weak, plus a strong base like sodium hydroxide. We would do a double replacement reaction and we would form water, and then we would also get the salt sodium cyanide. So sodium cyanide is a basic salt. Now let's break it apart into its components. We just learned that the sodium ion is the cation, the metal cation from a strong base. So the sodium part of sodium cyanide is neutral. So it's not the sodium that's contributing any basic properties. The Cn- or the cyanide anion, though, that is the conjugate base of a weak acid. The conjugate base of a weak acid is also a weak base itself. So that Cn- ion is what's going to be contributing to the pH being greater than 7 and it being slightly basic. So what happens is that cyanide anion actually will react with the other product, which is water, and it'll change the pH. This is known as hydrolysis. When one of your ions that you form can react with water and adjust the pH after the neutralization reaction, this is called a hydrolysis reaction that occurs second. So the reaction for this hydrolysis would be Cn- plus H2O. In this case, our cyanide is a weak base and our water is an acid. So our acid would contribute a proton to our base, and water's conjugate base would be hydroxide. So the cyanide ion will react with water further and form a little bit of its conjugate acid, hydrocyanic acid, and some hydroxide ion. This is how the pH gets changed after that neutralization reaction. There are a lot of ions that will yield basic solutions. All of them are anions, so they all have a negative charge. They come from weak monoprotic acids. So some examples are cyanide, fluoride, acetate, carbonate. If you look at your acid-base ionization chart, now we're going to be interested in everything below the hydronium ion. These are all going to be weak acids, all the way up until water. Now, the conjugate base of any weak acid is a weak base itself. So for example, if we look at hydrofluoric acid, its conjugate base is the fluoride anion. And if we have fluoride in a salt that's formed, that fluoride anion can react with water and it can function as a base. If we find our hydrocyanic acid, HCN's down at the bottom here, we can see its conjugate base is the cyanide ion, and that is a weak base. So having that cyanide ion in a salt will allow that cyanide to further react with water. So there's a lot of these on here. We could have benzoic acid, that's a weak acid. If we have its conjugate base in a salt, benzoate ion, that can further react with water as well. So basically, any of the anions that are formed from the acid-base neutralization reaction, as long as they are the conjugate base of a weak acid. All of those anions will react with water after in a hydrolysis reaction to give you a basic solution. We'll come back and talk about HCO3- after we learn about salts that give acidic solutions, because it's kind of an exception to the rule. Salts that give acidic solutions. So this would be from the reaction of a strong acid, which is the stronger partner, and a weak base. That'll give us an acid salt. An example is hydrochloric acid plus ammonia, and that would form ammonium chloride. So ammonium chloride has two components. It has NH4+ as the cation, and it has Cl- as the anion. So if we find chloride on our acid-base ionization chart, chloride is at the top here. It's the conjugate base of a strong acid, and therefore it's going to be neutral. So the chloride component isn't what's causing the acidity, so it must be that ammonium ion. The conjugate acid of any weak base is also a weak acid. So that ammonium ion in this case can react with water in a hydrolysis reaction. So the ammonium ion is right here, and it's in that weak acid section of our acid-base ionization chart. So it itself is a weak acid that will react with water. Therefore, having ammonium in a salt will cause your solution to be acidic. So how the ammonium could react with water, you'd have NH4+ plus H2O, since it's a hydrolysis reaction. Anytime you have hydrolysis, it's some anion or cation reacting with water. The ammonium would be the acid, the water would be the base, so we would form H3O+, and we'd be left with NH3. So after our neutralization reaction, ammonium would react with water to form some hydronium ion. This is going to cause the pH of a solution to be less than 7 and slightly acidic. Conjugate bases of polyprotic acids from their first association are also salts that will give acidic solutions. So imagine that we have sulfurous acid, H2SO3, which is a diprotic acid. When it dissociates in a stepwise manner and it loses its first proton, the conjugate base from sulfurous acid is HSO3-, the hydrogen sulfite ion. Hydrogen sulfite could be an acid or a base. You'll find it in two locations on your acid-base ionization chart. It has a proton that it could donate, and it also has a negative charge where it could accept a proton. So if we look up the Ka and the Kb for the hydrogen sulfite ion, the Kb is 8.3 times 10 to the negative 13th, and the Ka is 6.2 times 10 to the minus 8th. In this case, the Ka is greater than the Kb. Since the Ka is larger, it'll act as an acid instead of a base. So if you form a salt that contains the hydrogen sulfide ion in it, it's going to react further with water in a hydrolysis reaction, and it will form some hydronium ion and its conjugate base, which is sulfite, SO3 2-. So this causes the pH of the solution to be greater than 7. This is true for other polyprotic acids as well. Typically, the conjugate base that's formed when a polyprotic acid loses its first proton is still going to be an acid. And usually the Ka will be greater than the Kb, even though the species is amphoteric. So therefore, if that anion is present in a salt from a neutralization reaction, it'll undergo acid hydrolysis. The last type of ion that gives an acidic solution is hydrated small metal cations. So you might notice there are some weird names on your acid-base ionization chart, such as this hexa aqua iron 3+ ion listed on the acid side, or hexa aqua aluminum ion, hexa aqua copper 2+ ion, hexa aqua cobalt ion. There's quite a few of these. All of these are small hydrated metal cations. They're actually all complex ions. And these complex ions in water will actually contribute to the pH of the solution by forming a solution with a pH of less than 7. So they will give us an acidic solution. Let's take the hexa aqua aluminum ion for an example. In water, the aluminum 3+ ion becomes coordinated with 6 water molecules. That means that 6 water molecules will surround that Al3+ ion. So that gives us this hexa aqua aluminum ion. And there's no way that you could know that 6 water molecules surround that. That comes from looking at the subscript right here that there is a 6 after the water. So those water molecules are called ligands, and they hydrate or surround our small, highly charged aluminum 3+ ion. So in this picture right here, the orange spheres are our oxygens of our water. The white ones are our hydrogens. And the central one is going to be our aluminum ion. And the whole thing, the whole complex, still has a +3 charge because water's neutral. And aluminum is a group 3A metal and it forms a +3 charge. So what happens is, since aluminum is a small ion that has a high charge, it really pulls the electrons away from the water ligands. It pulls them away in these covalent bonds. It takes those electrons and drags it towards themselves. So it polarizes the bond between the ligand and the metal cation. And it makes it easy for water, another water molecule, to actually pluck a proton off of one of the ligands because those bonds are so polarized. So if we imagine we have another water molecule right here, and there's 2 lone pairs of electrons on it, what it can do is it can grab with one of its lone pairs one of the hydrogens away from one of the ligands on the hexa aqua aluminum ion. And this would be the same case for all of those metal cations. One of those protons gets abstracted from the water ligand, and the electrons in that covalent bond stay with the oxygen. So when water grabs a proton, it forms hydronium ions. So this is H3O+ over here. And now what we're left with is the conjugate base of that hexa aqua aluminum ion. Notice now we have this oxygen that actually will have an extra lone pair of electrons on it, and so that would have a partial negative formal charge on it. The aluminum would still be 3+ in the middle, so the overall charge of the complex ion, that's the conjugate base, now goes down from 3+ to 2+ because it lost a proton. It still has 5 complete water ligands surrounding it that were untouched, but now it has one that essentially has a hydroxide attached as one of the ligands. So all small metal cations will have a certain number of water ligands that surround them, most of them with 6 surrounding them. And in water, they interact with that water, allowing it to function as an acid and abstract one of the protons from the ligands. This is why they end up giving acidic solutions, because the product of that is hydronium ion. So the pH of it will be less than 7. So in summary, the following ions will give acidic solutions. Cations that are conjugate acids from weak bases, and the only species that's a cation that is the conjugate acid from a weak base is that ammonium ion. You can look at your acid-base chart and take a peek through there. Conjugate bases of polyprotic acids after their first association. So all of those are weak acids themselves because they still have a proton that they could donate. So if those anions are in a salt, that anion is going to be contributing some acidic properties to it. And then any small metal ions that have a high charge. So some examples are aluminum 3+, chromium 3+, iron 3+. You could take a look at your acid-base ionization chart to see how many of those metal ions that are formed with water ligands surrounding them. So they all will have some kind of a complex ion that forms that can interact with water. So all of those will give you acidic solutions if they're present in your salt. So the following is a summary table for acidic, basic, and neutral ions. You will not be given this on a quiz or exam, but you have to be able to understand how to read your acid-base ionization chart to determine if something will be an acidic ion, a neutral ion, or a basic ion. So in summary, our neutral ions that were anions, these were conjugate bases of strong acids. They did not interact with water and undergo hydrolysis. Neutral cations were the group 1A and 2A metal cations that were from the strong bases. For our basic anions, we had conjugate bases of weak acids. So the conjugate bases of weak acids were weak bases themselves, and they could interact with water and undergo hydrolysis to give you basic solutions. The only one that is an exception, and it's in italics here, is HCO3-. HCO3- is the conjugate base of a polyprotic acid, carbonic acid, from that first association. But that one actually has a Kb that's bigger than the Ka, so it actually is a basic anion that's formed. And there's no cations that contribute basic properties. For the last one, acidic, we had cations that were small metal ions that had a high charge. These are just an example of a few. And those formed complex ions in solution with water as a ligand around them. And those ended up giving acidic properties to our solution. Conjugate acids of weak bases that were cations, that would be the ammonium ion. That's pretty much the only one to know. And then anions, those could be conjugate bases that are formed from the dissociation from the first step of a polyprotic acid. So all of those have a proton that could be donated again, and they can function as acids themselves. So let's try putting all of this together. Classify each of the following salt solutions as acidic, basic, or neutral. So we're imagining that we take this salt and we dissolve it in water, and what would the pH be essentially? So for A, we have potassium bromide, and we want to look at each component separately. Potassium is K+, and bromide is Br-. The potassium ion would be a group 1A metal, which would be the metal cation from a strong base. So this is going to be neutral. And the bromide anion, that's the conjugate base of a strong acid, hydrobromic acid. So it's a really weak base. So the bromide anion is also going to be neutral because its acid is a strong acid. So we have a neutral cation and a neutral anion, so together this solution will be neutral for potassium bromide. B, we have sodium nitrite, NO2. So we have the sodium ion that's contributing, and then we have the nitrite anion, NO2 minus. Sodium is a group 1A metal, so it's the metal cation of a strong base, something like sodium hydroxide. And so it's going to be neutral. And our NO2 minus, that would come from an acid like HNO2, which is nitrous acid. That's a weak acid. So nitrous acid is weak, and that means that its conjugate base is a weak base. So since NO2 minus is a weak base, it will contribute basic properties. And since we have one that's neutral and one that's basic, overall the solution will have a pH of greater than 7 and be basic. C, we have ammonium perchlorate. So we have the NH4 plus ion, and our anion of this salt is ClO4 minus. If we start with the perchlorate anion, that comes from the acid perchloric acid, HClO4, and that's a strong acid. So since we have the conjugate base of a strong acid, the perchlorate anion is going to be neutral. And our ammonium ion, that is a cation that is a weak acid. So since the ammonium ion is weakly acidic, it'll contribute acidic properties to our solution. So overall, ammonium perchlorate will give us a pH less than 7. It'll be acidic. In D, we have barium nitrate. Barium is Ba2 plus ion, and nitrate is NO3 minus. The barium ion is a group 2A metal from a strong base such as barium hydroxide, so it'll be neutral. Nitrate would come from HNO3, which is nitric acid, and that's a strong acid. And so strong acid will give us a very, very weak conjugate base, and so it is essentially neutral. So something like barium nitrate in water will truly give us a neutral solution with a pH equal to 7. And lastly, E is ammonium cyanide. So we have NH4 plus and then Cn minus. NH4 plus is a weak acid itself, the ammonium ion, so this will contribute acidic properties to the solution. And cyanide, that comes from hydrocyanic acid, HCN, which is a weak acid. So the conjugate base, Cn minus, is a weak base. It'll contribute basic properties. So now we have something that contributes acidic properties and something that contributes basic properties. We have to decide who's going to win. So we're going to look at the Ka and the Kb for each of these. So Ka for the ammonium ion is 5.6 times 10 to the negative 10th. And the Kb for the cyanide anion is 2.5 times 10 to the negative 5th. So in this case, the Kb is greater than the Ka. Therefore, the solution will end up being basic because the hydrolysis of the cyanide anion will trump the hydrolysis of the ammonium cation. Let's try another example. Classify the following solutions as acidic, basic, or neutral. In A, we have iron 3 chloride. So our cation component is Fe3+, and our anion component is the chloride anion, Cl-. Chloride is the conjugate base of a strong acid, hydrochloric acid, so it's going to be neutral. And Fe3+ is a small metal cation that will form essentially a hydrated metal ion that'll have water ligands surrounding it. So this is going to be acidic, and we have one that's acidic and one that's neutral. So overall, iron 3 chloride will be an acidic solution in water. B, we have calcium hydrogen sulfate. So calcium is calcium 2 plus ion, and our anion is HSO4 minus, the hydrogen sulfate ion. Calcium is a group 2A metal that is a metal of a strong base, such as calcium hydroxide. That's going to be neutral. And the hydrogen sulfate ion is the conjugate base that's formed when H2SO4, or sulfuric acid, loses its first proton. So it's the conjugate base from the dissociation, the first step of the dissociation of a polyprotic acid. And it itself is a weak acid because it still has another proton that it could donate. So this is going to be acidic. So overall, we have neutral and acidic. The acidic will win. We're going to end up having an acidic salt here. Lithium acetate, that'll be made up of lithium ion and acetate anion. So lithium is a group 1A metal, and that would come from a base like lithium hydroxide, so that's going to be neutral. And the acetate anion is from a weak acid, which is acetic acid, HC2H3O2. So it itself is a weak base. It'll be a basic anion. So that's going to win in this case, and the solution will be basic. And lastly, we have aluminum fluoride. So aluminum is Al3 plus ion. Fluoride is F minus. Aluminum 3 plus is another small metal cation that will get hydrated, so it's acidic in solution. And the fluoride anion, that comes from HF, hydrofluoric acid, which is a weak acid, so its conjugate base is a weak base. Fluoride will be basic. And when we have this situation where one is acidic and one is basic, we have to compare the Ka to the Kb. So when we look up the Ka, we're not just going to find Al3 plus on our chart. We're going to find that hexa aqua aluminum ion that we need the Ka for. So that is 7.9 times 10 to the negative 6th. And the Kb for the fluoride anion is 1.4 times 10 to the negative 11th. So in this situation, the Ka is greater than the Kb, and this will end up being an acidic solution because of that. Now that we learned how to identify if a given salt is acidic, basic, or neutral, for salts that are basic or acidic, we can also take this one step further and calculate the pH of a salt solution. So calculate the pH of a 0.1 molar solution of sodium cyanide. So just like we did before, if we break this up into its components, Na plus and Cn minus, we have the sodium ion, which would come from something like sodium hydroxide, so a strong base, it'll be neutral. And then we have the cyanide anion, which comes from a weak acid, hydrocyanic acid. So the conjugate base of a weak acid is weakly basic. So that cyanide anion is going to be basic and contribute to changing the pH of the solution. It'll interact with water in a hydrolysis reaction. So the first thing we have to do when figuring out the pH of a salt solution is actually write that hydrolysis equation. So what hydrolysis means is an anion or a cation reacts with water, and it will change the pH when it does so. So the sodium ion isn't going to react with water because it's neutral, but the cyanide anion will. So we're going to have Cn minus plus H2O, and what are our products going to be? The cyanide is functioning as a base, which means water is functioning as an acid. So when our acid donates a proton to our base, we form HCN, hydrocyanic acid, and we're left with OH minus, hydroxide. So we have essentially an equilibrium of a weak base and water set up, because cyanide is weakly basic. So we're going to make an ice table. And our initial concentration of our salt was made up to be 0.1 molar. Well, when something like sodium cyanide dissociates in water, it's going to break up to give Na plus and Cn minus. The stoichiometry of our equation is 1 to 1 to 1. So if we know the sodium cyanide was made up to be 0.1 molar, the sodium in the solution, the sodium ions that are produced from the dissociation are also 0.1 molar. And the cyanide ions that are produced are 0.1 molar as well. So we can plug in for our cyanide ion, 0.1 molar. We're going to ignore our water because that's a pure liquid, so it's not in our equilibrium expression or our ice table. Initially, before any cyanide has undergone hydrolysis, we have 0 HCN and 0 OH minus. When our cyanide reacts with water, it's going to go away by minus X. And when we form our HCN, that'll be formed by plus X. And by plus X for our hydroxide, because everything is 1 to 1 to 1 to 1 in our hydrolysis reaction. Our equilibrium will be 0.1 minus X for our cyanide, X for our hydrocyanic acid, and X for our hydroxide ion. So once we write our hydrolysis equation, this is now just like any other weak base pH calculation. We can write our equilibrium expression. Since we have a weak base in water, it's going to be Kb is equal to HCN concentration times OH minus concentration all over Cn minus concentration. If we look up the Kb for Cn minus, it's 2.5 times 10 to the negative fifth. So you're going to want to find that on your chart. And once again, you have a small value here, less than 10 to the minus fourth. And so we get to ignore that minus X to simplify our algebra here. So now substituting everything in from our ice table, we got our Kb for cyanide, 2.5 times 10 to the minus fifth. We're going to have X for our hydrocyanic acid and X for our hydroxide ion, all over our initial concentration of our cyanide anion, which was 0.1 molar, the same as it was made up for the sodium cyanide solution. So that'll be X squared over 0.1. And we're going to multiply both sides of the equation by 0.1, so it'll give us X squared is equal to 2.5 times 10 to the negative sixth when we do that. And then we'll have to take the square root of both sides to give us X, which that comes out to 1.58 times 10 to the negative third molar. And we're trying to figure out the pH, so X in this case was equal to the hydroxide ion concentration, which that's what's important for us, because from our X now, we're going to have to calculate our pOH, which will be the negative log of our hydroxide ion concentration. So negative log of 1.58 times 10 to the negative third gives us our pOH, which comes out to about 2.80. And then our pH of our sodium cyanide solution will be the pKw minus the pOH. So we'll have 14 minus 2.80, which comes out to being 11.20. And we should have expected our pH to be greater than 7 because we said that we had sodium that was neutral and the cyanide was a basic anion. So we got 11.2, our pH was greater than 7. That's kind of your final check there to make sure that your math worked out okay to what you expected your salt to be. Let's try another pH calculation of a salt solution. Calculate the pH of a 0.1 molar ammonium chloride solution. So ammonium chloride, if we break it up into its anion and cation, that's a salt, and ammonium, NH4+, is a weak acid, so it's going to be acidic. And the chloride anion is the conjugate base of a strong acid, HCl, so it's going to be neutral. So the neutral chloride anion isn't going to interact with water, but the acidic ammonium ion can interact with water in this solution and undergo hydrolysis. So this is going to be an acid hydrolysis reaction that we have to write. So whenever we figure out which anion or cation is interacting with water, we then have to write our equation. So we're going to have ammonium ion plus water, because it's hydrolysis, and we're going to have to think about our species, what they're acting as. The ammonium ion's acting as an acid, which means the water's acting as a base. So our acid will be a proton donor to our base. When water picks up a proton, it forms hydronium, that's its conjugate acid. Plus, when our ammonium loses a proton, it'll form ammonia, its conjugate base. Next, we're going to make our ice table. So our initial concentration of ammonium ion comes from our concentration of our salt solution. So when NH4Cl is put in water, it'll dissociate into ammonium ions and chloride anions. The stoichiometry is 1 to 1 to 1 in this case. We had a 0.1 molar solution of ammonium chloride that it was made up as, and that will give us 0.1 molar ammonium ions and 0.1 molar chloride anions. So we're just really interested in the concentration of the ammonium ions because they're the only ones that interact with the water. So that's our initial concentration is 0.1 molar. We're just going to cross off our pure liquid water and ignore that for now. Initially, there's no hydronium formed and no ammonia formed. The ammonium will go down by X, hydronium will form by X, and ammonia will form by X. At equilibrium, we're going to have 0.1 minus X, and then X for hydronium and X for ammonia. Our equilibrium expression, we're going to write next, and that's going to be K sub A is equal to the concentration of H3O plus times NH3 all over the concentration of ammonium ions NH4 plus. We have to use the Ka for NH3 because it's acting as an acid with water. So when we look up the Ka for our ammonium ion off of our chart, we'll find 5.6 times 10 to the negative 10th power. So it's a fairly weak acid. It's very small, which is normal. So we're going to be able to, once again, ignore that minus X and simplify. So we have 5.6 times 10 to the negative 10th is our Ka for ammonium is equal to X for our ammonia and X for our hydronium all over 0.1 molar. That was our concentration of our ammonium ion initially. That'll be X squared over 0.1 molar. X squared is equal to 5.6 times 10 to the negative 11th when we multiply both sides of the equation by 0.1. And then we'll square root both sides to give us X. X comes out to being 7.48 times 10 to the negative 6th. And X was equal to our H3O plus concentration. So this time we have our hydronium ion concentration directly, so we can calculate the pH right away by taking the negative log of the hydronium ion concentration. So negative log of 7.48 times 10 to the negative 6th, that gives us a pH equal to 5.13. And so because ammonium was an acidic cation, the pH was less than 7, like we would have expected it to be. Really, once we wrote our hydrolysis equation, then it was just like doing the pH calculation for any other weak acid. Same thing with the first example with the basic salt. Once we wrote that hydrolysis equation and identified which component was basic, it was just like doing any other calculation of a weak base. So the important part is being able to look at that salt and break up the cation and anion component, figure out what is contributing to the hydrolysis, and then write that hydrolysis equation.